video, we'll solve this question. We'll find the area of the region enclosed by these two curves, x equals minus y squared plus 2 and x equals minus y. Now, I'm going to do it first the way it should be done, and I'll do it using the second technique, the second way of slicing, just to show you why it would be more complicated. Alright, let's try this. Since the curve we're given is x equals a function of y, I should use, that's right, horizontal slicing. Now, whatever method you choose to use, you should always find the intersection points, and you should always give a sketch of the region, making sure the right functions are on top and underneath, the right functions are right and left, just so that your integral is set up properly. Alright, so step 1. So I want to find all points that are on both curves. Since x is isolated in both, I'll just set them equal. And so we get y squared minus y minus 2 is 0. That's y minus 2. Y plus 1 is 0. So I get 2 points. I get y equals 2 and y equals minus 1. Let's find the x values. That's going to make it easier to put on the graph. So if y equals to 2, x would be minus 2, so the first point is minus 2, 2. I'm using x equals minus y because that's the fastest. If y equals minus 1, then x will be minus y, which is 1. So I end up with 1 minus 1. So I have 2 intersection points. That means that I probably have a single interval. Second point, I'm going to figure out which curve is left and right. Since I'm using horizontal slicing, I really want to know which one's right or left. Top and bottom is not as important at this point. All right. Step 2. Right or left. So I only care about this region between minus 1 and 2, so I'm going to plug in a value of 1 in between those two. So let's say y equals 0. I'm going to have, for one curve, I'm going to have 2. And for the other curve, I'm going to get 0. So the one with the biggest x value, that one will be further right. The one with the smallest one will be further left. We're ready to sketch. Notice that if you actually know how to sketch these curves, you don't need to do the second part, because the way you sketch it was going to tell you which curve is right and left, but that shows that you don't actually need to be able to sketch all these regions. Alright, so let me put my intersection points first. So I have minus minus 2 and 2. So 1 minus 2 and 2. And I have 1 and minus 1. Now your sketch doesn't have to be precise. It does have to pass through these 2 points and have the right side and the correct left side. But let me sketch it nicely so that our job in the second part will become easier. So x equals minus y, that's a straight line through these 2 points. Then I have minus y squared plus 2. Minus y squared plus 2. So it's going to look like this. So it's a parabola sideways, and it has a vertex here, so it's going to look like this. All right, so here's my region. My horizontal slicing will be like this. And notice that wherever I place that green line, its right side will be on blue, its left side will be on red. So right is always blue, left is always red, and I don't have to change halfway through my integral what curve is right, what curve is left. That means that when I set it up, because I'm using horizontal slice, I'm using right minus left. Right, we said, will always be the blue curve, so that's minus y squared plus 2. Left will always be the right curve, so that's minus y. And so I'll be integrating minus y squared plus y plus 2. And now I need the y values. The lowest point is here. The lowest y value is minus 1. The highest one is up here with the 2. So my bounds will be from minus 1 to 2. And make sure you put it at every step. All right, so this is the integral that will give us the right value. And that value is 9/2. Alright, so if you choose horizontal slicing, this is it. Now let's do it with vertical slicing, just to show you that it's still doable in this case, but it is a bit more involved. There's a bit more algebra, and there are 2 integrals instead of 1. I'll leave the sketch up because we still need it. So let me erase that board. If you want to spend more time looking at this, you can always stop the video. we use vertical slicing, we have to write the curve as y equals a function of x. And so for both of these curves, I'm going to have to isolate y. So in this case, don't forget the plus or minus when you get rid of a square. In this case, I don't have a single function. I have two of them. I have y equal the square root of 2 minus x, and y equals minus the square root of 2 minus x. For the second curve, it's going to be easier. Y is just minus x. So in this case, I do get a single curve. I get y equals minus x. Let me color label them. So y equals minus root of minus x plus 2. And I have y equals minus x. So already you can see it's a bit more involved because I don't have two curves that intersect in 2 points. I have 3 different curves to think of. And so if you're solving algebraically for the intersection points, you'll have 3 intersection points to solve for. We already have the graph, so let's just look at the graph and see where these curves are. Alright, so the red curve was x equals minus y. It's now y equals minus x. So this here is y equals minus x. The blue curve was x equals minus y squared plus 2. It splits up as 2 different curves. Notice that in this case, y is positive. So the part of the curve where y is positive will be y equals the square root of 2 minus x. The part of the parabola where y was negative, that will be y equals minus the square root of 2 minus x. So you could do this algebraically, but since we've already graphed it, let me just do it geometrically. So we still have those 2 intersection points here, but now we have a third one. An intersection point between these 2 curves, that's really the vertex of the parabola, and that intersection point is 2, 0. Alright, so at this point we have the graph set up the way we need it for vertical slicing. We know the curves is y equals a function of x. We have all intersection points, so we're ready to set up the integral. Now if I draw my slicing here, so vertical means stick standing up. I'm going to get sticks from blue to red all the way here. So all of this part will have top is blue, bottom is red. Then these little sticks will have top is blue and bottom is green. So you can see it also as the bottom curve uses the red formula all the way here and then switches to the green one. So when I set up my integral, I will not be able to write a single formula for bottom, so I'll have to split the integral so I can write an algebraic formula for bottom. Alright, so A to B, top minus bottom. The smallest x is over here at -2. The biggest x is over here at +2. Like I said, I can't write a one expression formula for bottom, so I'll split it. I'll go from -2 all the way to 1. So top would be blue. And bottom will be red. So that integral will give us the area of the part of the region that's on the left of x equals 1. And then from 1 to 2, top will still be blue. You can see these orange sticks are going from blue to green, so top will still be blue. Bottom this time will be green, so green is -2 minus x. And so what I get is these two integrals. If you compute them and add their value, you will get the area of this region, and so you will get the same answer we got in A. You'll get 9/2. Alright, so hopefully you can see this is doable. It's fine, it's just a bit more complicated. It's more complicated in two ways. It's more complicated first because you have to yourself isolate y in all the curves. If you're using the horizontal slicing, this isolation was already done. You already had the curves given as x equals a function of y. So why go through the extra step of isolating yourself when it was already done for the other method? Now the second way this is more complicated is because bottom switches from red to green. That means when I set up the integral, I'll have to split it in two different ways because bottom doesn't have a single formula. It has the red one and the green one, and so I get two different integrals. And if I actually computed them, that'd be much longer than just computing the one.